Okay, exam review for Chapter 6-7. This is a system of equations. It's got three variables. It's got three equations. We need to choose a variable to eliminate. So choose two equations to eliminate a variable, and then choose two more equations to eliminate that same variable. So looking at this, notice a 3x here in this middle equation and a 3x here in the bottom equation. If this middle equation were multiplied by -1, it would become -3x minus 2y minus z is equal to +2. Bottom equation could stay the same, 3x plus 4y minus 2z equals 5. Now adding these two equations together, x is going to eliminate. -2y plus 4y is 2y. -z plus minus 2z is -3z. And 2 plus 5 is 7. So now we have an equation in terms of y and z. What we're going to need to do next is choose two more equations that eliminate the same variable. So here we eliminated x. We're going to have to eliminate x from another one of these two equations. So if we choose the top two, for example, this is a coefficient of 4, this is a coefficient of 3. The least common multiple is 12. So I'm going to multiply the top equation by -3, the bottom equation by +4. What that's going to do is give a coefficient of -12x here, a coefficient of +12x there. So those two equations are going to become -12x plus 9y plus 3z is equal to -30. That middle equation is 12x plus 8y plus 4z is equal to -8. Adding those together now, again x's cancel. 9y and 8y add to 17y. 3z plus 4z is 7z. That equals -38. Now we have two equations here in terms of the same variable, y and z. So now we can combine those. So I'm going to take this equation here and combine it with this one. 17y plus 7z equals -38. Now we need to eliminate a variable from here and solve for the remaining variable. So we could eliminate any variable here. We could, for example, try to eliminate z. So between -3 and 7, the least common multiple is 21. So this would need to be multiplied by 7. This would need to be multiplied by 3. So this equation now becomes 14y minus 21z equals 49. 3 times 17, or 3 times 17y, 3 times 17 51y plus 21z, and 3 times -38 is -114. So the z's cancel when we add these together. 51y plus 14y is 65y. Z's gone. And 49 minus 114 is -65. Divide both sides by 65 to get y equals -1. So now, moving backwards through this, plug y into one of these equations in terms of y and z. So I'm going to choose this equation here. So that's going to be 2 times -1 minus 3z equals 7. 2 times -1 is -2. Add that to 7 to get -3z equals 9. So z equals -3. So now we know z and we know y. So you can plug that into one of the original equations now to find x. So bottom equation, for example, 3x plus 4y minus 2z equals 5. Now 4 times -1 is -4, -4, and then -2 times -3 is 6, -4 plus 6 is 2. Subtract 2 from 5 to get 3. So x equals 1. So your solution is to point 1, comma -1, comma -3. Alright, question 2. Same type of thing as a system of equations, 3 variables, 3 equations. So we approach it the same way. Notice right off the bat, right here we have a -y and a positive y, so adding equation 1 to equation 2 would result in 3x, y's cancel, 5z plus 4z is 9z, -2 plus 2 is equal to 0. So if we multiplied this middle equation by -4, that's going to cancel with that positive 4y, so that's going to become -8x minus 4y minus 16z is equal to -8. And we're going to get 2x plus 4y minus 2z equals positive 8. Add y's cancel, -6x minus 18z equals 0. So now we need to make a system of equations with these two new equations here. Multiply bottom equation by 2. So what we're left with is the statement 0 equals 0, which is true. There are no variables to solve for, so we can't solve for a unique solution, but there are infinitely many. There are infinitely many solutions, and now it says if there are infinitely many solutions, then state the solutions in terms of a parameter t. So we need to let z equal that parameter t. Now parameter just means that t can take on any real number, and if t can take on any real number, that means z can also equal any real number. Our task now is to define x and y in terms of t. So now that we know that z equals t, we can go back up into this equation here to find the value of x in terms of t. So if z is equal to t, then 9 times z is equal to 9 times t. So 3x plus 9t is equal to 0. Subtract 9t on both sides and you get 3x equals -9t. Divide by 3 and get x equals -3t. And now we go back up to one of the original equations. Top one, for example, we need to solve for y. So if x is -3t, then we're going to have -3t minus y plus 5t equals -2. -3t plus 5t, that's 2t, so -y plus 2t equals -2. So rearranging this slightly and getting y by itself would give the equation y equals 2t plus 2. So that's the final variable we needed, y equals 2t plus 2. So those are the values of all three of the variables. Z equals t, x equals negative 3t, y equals 2t plus 2. So your solution, x is negative 3t, y is 2t plus 2, z is equal to t. Okay, a little bit of a more simple system of equations to solve. It's got only two variables. So I'm going to try to eliminate the y variable. Between a negative 2 and positive 3, this is going to multiply 6. So I'm going to multiply this by 3, multiply that by 2. So we get the equation 24x minus 6y equals 15. Here we have negative 24x plus 6y is equal to 14. Now, the variables cancel, so there's a 0. And the statement is 0 is equal to 29. It's not a true statement. There aren't any variables to solve for anymore. This is an example of a system of equations with no solutions. Question 4. This is a system of nonlinear equations. This is a parabola. This is a linear function. So there are a number of ways we could solve this. For example, this bottom equation could be rearranged and solved for x. So this bottom equation could be written as x equals y minus 3 So if this x equals y minus 3, this x here equals y minus 3. So y minus 3 can be substituted in for that x. So instead of x squared, it's y minus 3 squared plus y equals 9. Y minus 3 squared is y squared minus 6y plus 9. And then we have the plus y equals 9. Subtract 9 on both sides. So you have y squared minus 5y is equal to 0. Factor out a y and get y minus 5 is equal to 0. So y is equal to 0 and y is equal to 5. Now these are two distinct y values, which means there's going to be two x values paired up with these y values. So to find the value of x, we place the values of y in here. So if y is equal to 0, then 0 minus 3 is negative 3, so x equals negative 3. If y is equal to 5, then 5 minus 3 is 2, so x equals 2. So two solutions are negative 3 comma 0 or 2 comma 5.
Okay, partial fraction decomposition. This comes from chapter 6, section 4, I think, 6.4. There was a lot to that section. You have to remember the different cases of what the form of the partial fraction looked like. And the form depended on what the denominator looked like in factored form, and that's important. On both of these examples, the denominators are already in factored form. That might not be the case on the test. So you have to make sure that the denominators are factored. So anyway, in part A, the factors are both linear and they're both unique or distinct. So in that case, the form of the partial fraction is A and B. We have an A and a B piece, and then the factors form the denominators. And before I get into solving this, I just want to show you how that differs here on part B. The factors are both linear, but the difference is this x minus 2 is repeated. So the forms of the fraction, the partial fraction, are going to be a little bit different. You have an A for this piece right here, but because there's two of these, we're going to have a B and a C. And over here, the A, that's going to be with the x minus 1, And then with the repeated linear factor, since it's repeated twice, you have x minus 2 and x minus 2 squared. So these are the forms of the partial fractions. Now up here on part A, after you make the form of the partial fractions, you multiply each side of the equation by the lowest common denominator. In this case, it's x minus 5, x plus 2, something over here. So that cancels out the denominator, and you're left with 7x plus 7. Now when the LCD distributes to that term, the x minus 5s will cancel, and so you're left with a times x plus 2, and then when it distributes here, the x plus 2 would cancel, so b multiplies x minus 5. Now you have to keep in mind what it is we're solving for. We're not solving for x, we're solving for the values of a and b. So it doesn't really matter what x equals. We can let x now equal whatever we want. The way this was presented in the discussion was to choose convenient values of x that would make either this a term disappear or this b term disappear. For example, if you plug in a negative 2 right here for x, negative 2 plus 2 is 0. 0 times a is 0, so the a would disappear. So I'm going to let x equal negative 2 for my first convenient value of x. Plug in a negative 2 for all the x's. So if you plug in a negative 2 right here for this x, that's negative 14 plus 7, which makes a negative 7. Now the negative 2 in place of this x causes this term to disappear. Negative 2 minus 5 is negative 7. Negative 7 times b is negative 7b. If you divide by negative 7 on both sides, you get a value of b where b equals 1. Now, there's another convenient value we can choose here. If I've allowed x to equal 5, then 5 minus 5 is 0, so I'm also going to let x equal 5. 7 times 5 is 35, plus 7 is 42. Now over here, 5 plus 2 is 7. 7 times a is 7a. And then the 5 on this side, 5 minus 5 is 0, 0 times b is 0, so that term will disappear. Divide by 7 on both sides, so you get that a equals 6. So now that we have the values of a and b, we can finish the forms of the partial fraction. Instead of a over x minus 5, it's 6 over x minus 5 plus 1 over x plus 2. Now part B, we already have the form of the partial fraction set up. So the same first step as what we did on part A, we're going to multiply each side of the equation by the LCD. So on this side, x cancels out the denominator. Now the LCD has to multiply each of these pieces. So when this LCD multiplies all the way over to this first fraction, the x minus 1 here and the x minus 1 there will cancel. So a multiplies x minus 2 squared. Now when the LCD multiplies to the b term, this single x minus 2 on the denominator here would cancel with one of these x minus 2s. So you'd have one of the x minus 2s times an x minus 1 that multiplies the b. So it's plus b times x minus 1 times x minus 2. Now when the LCD multiplies in the c term, the x plus 2 squared cancels with the x plus 2 squared. So c multiplies x minus 1. Now we do a similar thing that we did on part A. We have to choose some convenient values of x that would make some of these terms disappear. First one that comes in my mind right now is let x equal 2. Just taking a look at this value right here, 2 minus 2 would be 0, so this term would disappear in that case. So if x equals 2, then right here, 2 squared is 4 times 4 is 16. The a piece of this equation would disappear. And so would the b part, because here if x is 2, 2 minus 2 is 0. 0 times the rest of these values will still be 0, so the b disappears. And over here, 2 minus 1 is 1. 1 times c is c. So right off the bat, we get that c is equal to 16. Now another convenient value we can choose is let x equal 1. If you take a look right here, 1 minus 1 is 0, so the c term disappears. And then over here for b, 1 minus 1 is 0. 0 times b times x minus 2, that disappears to 0. So over here on the left side, if x equals 1, 1 squared is 1 times 4 is 4. And then over here, 1 minus 2 is negative 1, but negative 1 squared is 1. 1 times a is a. So a equals 4. Now, this next part, you have to get a little creative. We've used the only two convenient values, quote unquote, of x that would make these terms disappear. Now, remember what I said a little bit earlier. It doesn't really matter what x equals because we're solving for a, b, and c. So you can really let x equal whatever you want. So I'm going to let x now just equal a random number. I'm going to choose 0. But I'm also going to let a and c take on their known values. I'm going to let c equal 16, and I'm going to let a equal 4. If you plug in a 0 for x, a 16 for a, and a 4 for a rather, and a 16 for c, then the only unknown in this whole equation would be b, and that's what we're solving for. So if x is 0, 0 squared is 0 times 4 is 0, so the left side of the equation is 0. Now remember, a was 4, x was 0, 0 minus 2 is negative 2 squared is 4, 4 times 4 is 16, and we don't know what b is, but x is 0, 0 minus 1 is negative 1, 0 minus 2 is negative 2, negative 2 times negative 1 is 2, 2 times b is 2b, and then over here, if c is equal to 16, and x is equal to 0, 0 minus 1 is negative 1, negative 1 times 16, negative 16, so those cancel, 0 is equal to 2b, and b is equal to 0, so we have the three values that we need. Now we can finish the partial fractions. We have 4 over x minus 1. Now, technically, since b is equal to 0, you could have a 0 over x minus 2, but 0 divided by anything is still 0, so you don't really need that middle piece. And then c is equal to 16, so 16 over x minus 2 squared. Now, question 6, this is just more practice with row operations. I've already given you the row operations to perform. If you were doing Gaussian elimination to reduce a matrix to row echelon form, you'd have to come up with the row operations on your own. But this is just for practice. We have negative 3 times row 1 plus row 2, and that's going to equal row 2. So let's do that one first. So negative 3 times this 1 is negative 3. Negative 3 plus negative 1 is negative 4. Then move over to the next column here. Negative 3 times negative 4 is 12. But 12 plus negative 6 is 6. And then move over to here. Negative 3 times this 3 is negative 9. Negative 9 plus negative 6 is negative 15. Move over to here. Negative 7 times negative 3 is 21. 21 plus 8 is 29. So that's the row operation that affects row 2. Now there's another one here that's going to affect row 3. So you have 2 times row 1 plus row 3 equals row 3. So now 2 times row 1 is 2. 2 plus negative 7 is negative 5. 2 times row 1 here is negative 8. Negative 8 plus negative 5 is negative 13. 2 times row 1 here is 6. 6 plus 6 is 12. And then 2 times row 1 here is negative 14. Negative 14 plus 8 is negative 6. Row 1 stays the same. And that would be the resulting matrix. This line right here, some textbooks in an augmented matrix put a line right here just to show where the equal sign would be. Since these are coefficients of variables, this is where the equal sign would be, and these are the numbers after the equal sign. So that line in the middle really doesn't mean much.
Okay, multiplying two matrices. First, we need to check that the multiplication is possible. This is a 2 by 3 matrix. That has 2 rows, 3 columns, so 2 by 3. This has 3 rows and 2 columns, so it's a 3 by 2. The inner dimensions tell you they have to match, so this multiplication is possible. The outer dimensions, 2 and a 2, are what this is going to result in. So it's going to result in a 2 by 2 matrix with 4 entries. This entry here comes from the first row, first column. So first row here, first column right here. So 3 times negative 1 is negative 3. Negative 8 times 8 is minus 64. And then negative 5 times negative 7 is positive 35. Now this entry here is second row, first column. So second row, first column here. 6 times negative 6, or negative 1 is negative 6. 6 times 8 is 48. And then 7 times negative 7 is negative 49. This entry here is the first row, second column. First row, second column here. So 3 times 10 is 30. Negative 8 times 3 is negative 24. And then negative 5 times 7 is negative 35. This is second row, second column here. Second row, second column. 6 times 10 is 60. 6 times 8, or 3 is 18. And then 7 times 7 is 49. So simplifying those numbers, as best you can without a calculator, I know it's tough. We're going to have negative 32, negative 7, negative 29, and 127. Question 8, find the inverse of a 2 by 2 matrix. So the formula is, given a matrix A, B, C, D, the inverse is 1 over AD minus BC, and that's a scalar multiplier in front of a matrix where you switch A and D and change the sign of B and C. So on this one, we need to find 1 over AD minus BC. So 1 over, now this is AD right here. That's 6. And we minus, this is B and C, so we minus negative 1. And then we switch the place of A and D here. So negative 2, negative 3. And then change the sign, change that to plus, change that to minus. So 1, negative 1. 6 minus negative 1 is 7, so it's 1/7 times the matrix. Negative 2, 1, negative 1. Negative 3. Solve the system of linear equations using matrix algebra. Matrix algebra means we have to set up a matrix equation, find the inverse of the coefficient matrix, and then multiply that on either side. So the matrix equation, these form the coefficients of the variables form the coefficient matrix. So the matrix is negative 3, negative 1, 1, negative 2. Now we have to have a variable matrix. And it equals this column 1 and 12. So what we're solving for is x and y. We need to get this xy matrix by itself. So we need to cancel or in some way undo this matrix in front of the xy matrix. So the only way to get rid of a matrix or to reduce it to 1 essentially is to multiply it by its inverse. So we need to find the inverse of this. But this matrix is simply the matrix from problem 8 here. We've already found the inverse. This is A inverse. If we multiply by A inverse over here, that matrix is gone. We'd have to multiply it by the inverse to the left side here. So the matrix xy is equal to this inverse matrix we already found, 1/7. So negative 2, negative 1, 1, negative 3, multiplied by this matrix, negative 1, 12. Now I would recommend that you multiply the two matrices together first and then times by the 1/7. So this is a 2 by 2 matrix, this is a 2 by 1 matrix. Multiplying a 2 by 2 to a 2 by 1 results in a 2 by 1. So it's just a single column with 2 entries. This entry comes from first row,
And first column, 2 times negative 1 is 2. 1 times 12 is 12. Second row, negative 1 times negative 1 is 1. Negative 3 times 12 is minus 36. So this is 1/7 times 14 over negative 35. Now times by 1/7 and you get 2 negative 5, and that equals x and y. So x is 2, y is negative 5. So the solution is 2, negative 5.
Number 10, evaluating a 2 by 2 determinant. The formula for a 2 by 2 determinant is AD minus BC. This is AD here, and then you subtract the BC product. So AD is 25 minus BC, which is negative 21. Minus a negative is the same as plus, so that's 46. 3 by 3 determinant is done so much a little more complicated. It's a little bit different. You need to expand across the row or down a column, and it doesn't matter which row or column you choose, but it is wisest to choose a row or a column that contains 0. So the top row, for example, contains a 0. So what you do is you consider each entry in that row that you've chosen. In this case, I've chosen the top row. That's what's called a cofactor. If you choose a cofactor, then you have to also find its minor. The minor is found by crossing out the column and the row that contains that cofactor. So you take the cofactor 8, multiply it by the discriminant of that minor matrix, 1, 3, 5, 9. And now we move on and continue with the next cofactor, find its minor. Now you have to follow a particular pattern when you're doing the 3 by 3 determinant. The pattern is plus, plus, minus, 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 or plus, minus, plus, depending on which row or column you're choosing. We chose the top row here, so I have to follow this pattern. We keep the first cofactor there, just whatever it is, positive. When we move over, though, we have to minus the next cofactor, which is negative 1, and now the minor, if we cross out the row and the column there, we're going to have a minor of 3, 8, 3, 9. I move over to the next one, and we add the next. This one tells us to add the next cofactor, but the next cofactor is 0, so it doesn't matter what its minor is. 0 times anything is 0. So this becomes 8 times the determinant 9 minus 15. Over here, negative or minus negative 1 is equals plus 1, and this is 9 times 3, which is 27, minus 24. 27 minus 24. 9 minus 15 is negative 6. It's 8 times negative 6. And then 27 minus 24 is 3. 8 times negative 6 is negative 48. Plus 3 is negative 45. Question 12, you're meant to take this matrix equation and write it as the system of equations from which this matrix equation came. So this top row here, these are coefficients of an x, y, z variable respectively, and it would equal negative 21. So this first equation is x plus 4y minus 3z is equal to negative 21. This middle row here are the coefficients of the next equation, negative 5x minus 3y plus z is equal to 20. Bottom row are the coefficients of yet another equation, 8x plus y plus 5z is equal to negative 13. It says specifically do not solve, so you just leave it. Question 13, using Cramer's rule to solve. Cramer's rule involves setting up a series of determinants and then dividing them to find your values of x and y, or z, however many variables you're looking for. So if it's 2 variables looking for, you need 3 determinants, d sub x, and d sub y. The determinant d is simply the determinant formed by the matrix of the coefficients of the variables. So this is negative 3, negative 1, 1, and negative 2. The determinant is going to be AD, negative 3 times negative 2, which is 6, minus negative 1, or minus the this cross product here, so it's minus negative 1,
and that's 7. Now d sub x, the subscript says we're going to take out the coefficients of the variable x that were there, and the reason we're choosing x variable because it says d sub x. You replace those with these coefficients, negative 1 and 12, so the matrix becomes negative 1 and 12, and then it has the same y coefficient, negative 1, negative 2. Now to find that determinant, a times d is 2 minus 12 times negative 1 is negative 12. 2 minus negative 12 is 14. Now, the determinant d sub y means you don't consider the coefficients that were originally there for y. You replace them with those. The x column stays the same, so it's negative 3 or 1, but now the y column becomes negative 1 and 12. The determinant is negative 3 times 12, which is negative 36, minus 1 times negative 1, so that's negative 1. Those turn into plus. Negative 36 plus 1 is negative 35. Now Cramer's rule says that your x value is d sub x divided by d, which is 14 over 7, which is 2. The value for y is d sub y over d, which is negative 35 over 7, negative 5, so your solution is 2, comma negative 5. Question 14 says to solve the system of equations using an augmented matrix and then reducing it to row echelon form. So we first form the augmented matrix using coefficients. For the top row we're going to have 1, negative 2, 1, and 1. For the middle row, be careful, there's a missing term, so you have to have that 0 there, and then 1, 2, 5. Bottom row are the coefficients here, 1, 1, 3, and 8. Now, the idea for row echelon form, the top row has to have a leading entry of 1, and then beneath it should be 0 and a 0. So we already have a 0 there, which is great. We need to get this to be a 0. You move over to the next column. Okay, in the second row here, this should be a 1. Right here should be a 1. We should get a 0 underneath that. Once we've accomplished that, we move over. We'll want to get this right here to be a 1. And that's the direction we need to head. So we need to describe a row operation that's going to take this 1 right here and reduce it to 0. So if we multiplied row 1 by negative 1, added it to row 3, and have that equal row 3. Negative 1 times row 1 is negative 1, plus 1 is 0. Negative 1 times row 1 here is 2. 2 plus 1 is 3. Here negative 1 times row 1 is negative 1 plus 3 is 2. Negative 1 times row 1 here is negative 1 plus 8 is 7. That's all that's been affected so far. So we have a 1 and a 0 and a 0. This is already a 1, which is great. If it weren't a 1, you divide by whatever you need to make it equal 1. But since it's a 1, we need to get a 0 beneath it. So what we're going to do is describe a new row operation. If we multiplied row 2 by negative 3 and added it to row 3, that's going to turn that into a 0. So negative 3 times row 2 plus row 3, that's going to equal row 3. So negative 3 times this 0 plus that 0 is still 0, so we have a 0. Negative 3 times 1 is negative 3, plus 3 is 0. Negative 3 times 2 is negative 6, plus 2 is negative 4. Negative 3 times 5 is negative 15. Negative 15 plus 7 is negative 8. Now this bottom row has a 0, 0, and a negative 4 and a negative 8. What that means is negative 4 is a coefficient of z. There aren't any coefficients of x or y, so really from here we can start figuring out some of the variables. This row tells us that negative 4z equals negative 8, therefore z has to equal positive 2. Now if you go back up a step to this row is the equation y plus 2z is equal to 5, but if we know that z is equal to 2, 2 times 2 is 4. If you take 4 from 5, you get that y equals 1. Now, this top row is the equation x minus 2y plus z is equal to 1. If z is equal to 2 and y is equal to 1, that's become x minus 2 plus 2 is equal to...
What we need to do is graph both of these and find the area that's been double shaded. So first thing I'd like to do is rewrite this. So y is greater than negative 2x squared plus 4, and let's say negative y less than or equal to negative x squared plus 8. Divide everything by negative. Get greater than or equal to positive x squared minus 8. Okay, these are both quadratic, meaning they're parabolas. This first one here is going to be upside down. Let's start with that one. Go up 4. That's where the vertex is going to be. And then we need a couple of other points, and since it's just greater than and not greater than or equal to, it's going to be dotted. And then we need to figure out where the shading is going to be. So if you plug in a test point, like 0, 0 right there, you end up with the statement 0 is greater than 4, which is false. 0 is not greater than 4, which means the test point I chose here, 0, 0, is not in the shaded region. So the shaded region is on the outside of the parabola right around here. Now I'm not going to shade that right now because it's going to get kind of messy. I'm just going to remember that that parabola is shaded on the outside. Now, this one here, I'm going to go down 8. And then we need a couple of other points. This one's a little bit wider. And it's greater than or equal to. Let's try that again. Greater than or equal to means it's going to be solid. And I need to choose a test point for that one to figure out where to shade. I'm going to use the same test point. So I would end up with the statement 0 is greater than or equal to negative 8, which is true. So what I need to do is shade on the part where the test point is, right there. So that's inside that parabola. So trying to combine these double shaded regions, I need the outside of the dotted parabola and the inside of the solid parabola. So get a different color here. That's going to be here in this area on the outside. And if we wanted to extend the line of this solid parabola, then we could shade a little more inside there. Okay. So what we need to do next, after we've got the graph there, the double shaded region, is it says label the vertices. That's where the graphs intersect. Remember, to find out where graphs intersect, you need to solve a system of equations. So if we go back here and rewrite that as 2x squared plus y equals 4, and x squared minus y equals 8. We already have opposite coefficients there for y, so we can add these, cancel y. 2x squared plus x squared is 3x squared equals 12. Divide by 3, x squared equals 4, so x equals plus or minus 2. So we have two values there. For x, we need to figure out the values for y. So if I take this top equation, for example, and plug in 2 for x, I'm going to get, if I plug in a 2 right there for that x, I'm going to get 2 squared, which is 4. 4 times 2 is 8. So 8 plus y equals 4. That means we get negative 4 for y. Now, if I want to plug in the negative 2, I'm going to use the same equation right here. Plug in negative 2 for x. Negative 2 squared is still 4. 4 times 2 is 8, so I get the same equation. 8 plus y equals 4, so y equals negative 4 again. So it looks like we've got 2 comma negative 4, and then over here, negative 2. All right. Question 16. We need to maximize the value of p using these given constraints. So this is what was called linear programming from section 5.5. So what we need to do is graph the system of linear inequalities and then figure out the feasible region. And then from the feasible region, we need the boundary points, or the corners, or the outermost parts of the feasible region. Then we would plug those x and y points into this objective function, see which one gives us the largest value. So these two here, x is greater than 0, y is greater than 0, all that tells us is that we need to graph in the first quadrant. Okay. Now this one here, x plus 2y is greater than or equal to 10. If we were to graph that, the x-intercept is 10. And remember, we find the x and y-intercepts. To find the x and y-intercept, you let y equal 0. To find the y-intercept, you let x equal 0. So if I'm going to find the y-intercept here, I'm going to let x equal 0, and we get 2y equals 10, which means y equals 5. And it's greater than or equal to right there, so that means it's a solid line. And I need to figure out where to shade on that line. So if I use my test point 0, 0 right there, I would plug in x and y as 0 for both x and y, and I'd end up with the statement 0 is greater than or equal to 10, which is not true. So on that one, I would be shading above the line. So I'm just going to put little arrows reminding me that I'm shading above that line. Now for this inequality, 3x plus 4y is less than or equal to 24. If I want to find the x-intercept, I let y equal 0, divide by 3, get x equals 8. So there's 8. Okay, and if I want to find the the y-intercept, I let x equal 0, and I get y equals 6. Okay, and with that one, if I wanted to use a test point 0, 0 right there, I let x and y equal 0, and I get the statement 0 is less than or equal to 24, which is true. So that means I'm shading below that line because it would be towards the test point. So below that line and above the first line, the double shaded region's pretty tiny here. It's this little sliver right here. So let me erase some things. So I needed to shade above this one, and then below the one I just graphed, which puts, yeah, the shaded area, whoops, right in there. Not a very big shaded region. So I need the boundary points of that. It's wherever that intersection point is, and then this point. So I need to know the location of that point. I need to know the location of that point, and I need to know the location of that point. Well, this one here is 0, 6. This one here is 0, 5. And where two graphs intersect, if it's not on an axis like these ones are pretty easy to find because it's right on an axis. But where two graphs intersect, you need to find the equation of those lines and solve the system. So that intersection point came from these two inequalities, so I need to turn them into equations. And then solve the system. So I would probably multiply the top one by -2, add these now together. That's going to leave me x, the y would cancel, and this is -20 plus 24, so that's x equals 4. Now if I take that top equation here and rewrite it, I would get 4 plus 2y equals 10, subtract 4 and get 2y equals 6, so y equals 3. So finding the value of p for each of those points, so I need the value of p at the point 4, 3, I need the value of p at the point 0, 6, and I need the value of p at the point 0, 5. Those 3 points represent the corners or the boundaries of that feasible region there. So it's going to be 200 times 4. So I'm just plugging these into the objective function there. Plus 500 times 3. That's 800. Plus 1500, which is 2300. For 0,6, this would be 200 times 0 plus 500 times 6. That's 0 plus 3,000, which is 3,000. And then for 0,5, that's 200 times 0 plus 500 times 5, 0 plus 2,500, 2,500, so it looks like 0,6 maximizes P.
Okay, 17 and 18. Both of these come from section 6.3. Right here, a chemist has 3 acid solutions. The question here is how many milliliters of each type of solution should be used. If there's 3 solutions and they're asking how many of each, that means we're going to have 3 different variables because we don't know how many of each. So we could say let x equal, we have to be extremely careful on how we define the variables. We can't just say x equals the 10% solution. That's not specific. What about the 10% solution? In this case, they're asking for how many milliliters of each, so we have to define our variables that way. X equals the number of milliliters of the 10% acid solution. Y is the number of milliliters of the 20% acid solution, and Z is equal to the number of milliliters of the 40% solution. Now we have to start gleaning out some information here. How many milliliters of each type should she use to make 100 milliliters total? So this chemist wants to have 100 milliliters, which is comprised of a combination of x, y, and z. So we know that x plus y plus z has to equal 100 milliliters. So there's a first equation. Now it says here that the 100 milliliters has to be 18% concentrated. So now we have to start talking about the concentration. So we're going to have 0.1, 10% of x, because the x solution is 10% concentrated. We're going to have 0.2 y plus 0.4 z, and here's where students make a very common but very costly mistake. A lot of students would want to just put a 0.18 right here, and that's incorrect, because if you look at how we've described it, it's a concentration multiplied by an amount. It's 10% of the number of milliliters x. Over here is 20% of the number of milliliters y. So right now all we have is a concentration. It's 18%. But 18% of what? And it's 18% of the 100 milliliters. Now, this one right here, if she has to use 4 times as much of the 10% solution as the 40% solution, so she's using more of x than she is of z. She's using 4 times as much of the 10%. So the problem with a phrase like this is students read it literally. They say, okay, there's a 4 times the 10%, so we have a 4x equals z, and they just read it too literally, and this is completely wrong. 4 times x doesn't equal z because x is already bigger than z in the first place, and if we multiply x by 4, now it's even bigger than z. If we want x to equal z, since x is already 4 times as big as z, you have to multiply the 4 over here by z to make it equal x. So that's the equation. X equals 4z. Now we have a system of equations. We have 3 equations, 3 variables. We need to solve this. Let's clean this up a little bit, though, especially this middle equation. Not like in these decimals. So first of all, 0.18 times 100, that's just 18. And then if we multiply that middle equation by 10, that's going to get rid of the decimals. So let's go to the x plus y plus z equals 100. And then if we multiply that middle equation by 10, we get subtract the 4z down here at this bottom equation, and we get x minus 4z equals 0. Now, we can solve this really using any method, not just methods in Chapter 6, but we could also use methods in Chapter 7. The matrices probably wouldn't be anybody's first choice, so I'm going to solve this using elimination. If you notice in this bottom equation, it's only in terms of x and z. Y is already known. So if we consider now these top two equations, if we eliminated y from these top two equations, that would give us an equation in terms of x and z that we could then combine with this equation in terms of x and z, and then solve for either one of those x's. So I'm going to multiply the top equation by -2. That gives me -2x minus 2y minus 2z equals -200. Combine that with the middle equation of x plus 2y plus 4z equals 180. That's going to give negative x plus 2z is equal to -20. So what I was saying earlier is now both of these equations are in terms of the same two variables, x and z, so we could solve this as a system of equations now. Negative x plus 2z equals -20, and x minus 4z equals 0. The x's are gone. 2z minus 4z is -2z equals -20, so z equals 10. Now we were clear on how we define z is equal to z. Z is the number of milliliters of the 40% solution. So that means we're using 10 milliliters of the 10% solution. It says right here they're going to use 4 times as much of the 10% solution, so that means that has to be 40 milliliters of the 10% solution. And then if there's only 100 milliliters that are going to be used total, we've already used 50 milliliters here, so the amount of y has to be 50 milliliters. Okay, question 18. There's 3 types of gas, and the question is asking how many gallons, specifically it wants how many gallons of regular, actually right here, how many gallons right here of each type of gas were sold. Since there's 3 types and they're asking for the number of gallons for each, we need to know the 3 different variables. So x is the number of gallons of regular, y then would be the number of gallons of performance, and then z would be the number of gallons of premium. So define the variables. Now we have to start setting some equations. Now it says right here on a particular day 6,500 gallons of gas were sold. It doesn't say what type of gas, it says total gas, 6,500 gallons. So total means you're going to add x plus y plus z, because that's the number of gallons of each type. If you add that all up, it's going to be 6,500 total. So now here it says the price. Regular is $3 a gallon, performance is $3.20 a gallon, premium is $3.30. Talk about the revenue generator. The revenue generated for that day was $20,050. So the revenue just from regular gas was $3 multiplied by the number of gallons sold. The revenue generated from performance is $3.20 multiplied by the number of gallons sold. And from premium, it's $3.30 multiplied by the number of gallons sold. Premium. And according to this, the total revenue is $20,050. We have another one of these tricky phrases at the end here. 3 times as many gallons of regular as premium were sold. You don't want to read this literally and make a literal equation of it. The number of gallons of regular is already 3 times greater than the number of gallons of premium. So in order to put an equal sign between x and z, they're not equal to each other. X is already 3 times larger than z. So in order for these to equal each other, you have to multiply z by 3 in order to make it equal x. So x is equal to 3z. So those are the 3 equations. Again, these decimals here aren't looking too good, so I'm going to multiply this middle equation by 10, so that becomes 30x plus 32y, this is the middle equation, plus 33z is equal to 200,500. Now this bottom equation, I'm going to minus the 3z over, and x minus 3z is equal to 0. It's a very similar situation as the problem above. You notice this bottom equation is only in terms of x and z. Y is missing. So I'm going to try to take the top two equations and eliminate the y variable. Now if you notice, there's a 32 coefficient in front of the y now in this middle equation. So if we were to take this top equation and multiply it by negative 32, that would allow us to eliminate y. So I'm going to multiply the top equation by negative 32. So it becomes negative 32x minus 32y minus 32z. And multiply 6,500 by negative 32, you get negative 208,000. So if we now add these two, the top two equations, we're going to get negative 2x plus z is equal to negative 7,500. If you now combine this equation right there, we have x minus 3z. And actually, what I'm going to do before I do that, I'm going to try to eliminate the x variable, so I'm going to have to go ahead and multiply this equation by 2. And then I'm going to bring it over here, so now it becomes 2x minus 6z equals 0. Add these together, we get negative 5z is equal to negative 7,500. Divide by negative 500z is equal to 1,500. So that's the number of gallons of premium. 1,500 gallons. Now I said there was 3 times as many gallons as regular, so if premium is 1,500 gallons, that means regular is 4,500 gallons. And there were only 6,500 gallons of gas sold that day. 1,500 and 4,500 is already 6,000, so that only leaves 500 gallons of performance.
This question 19 from section 6.3, finding the inverse of a 3x3 matrix. Sometimes not a quick process, so you just got to go real slow, be very careful. First step is to copy this matrix. So and then you make a little divider there, and then on the right side you have the identity matrix. And the goal is to do row operations to transform this side of the matrix into what this looks like. So I need to transform the left side of the matrix into identity matrix, and in doing so it's going to change these numbers into different numbers, and whatever that turns out to be, that's your inverse. So I need to get 1s along this diagonal right here and 0s above it and below it. That's my task. So I've already got a 1 right there, so I need to get a 0 here and a 0 there. So I can add negative 2 to both of those. So what I need to do is change this, change that 1 into a negative 2, and then add it to that row and add it to that row. So my first row operation, I'm going to do negative 2 times row 1. I'm going to add that to row 2. And that's going to become a new row 2. So let's try that. So starting there, negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. That's going to go in row 2. Now starting here, negative 2 times 2 is negative 4. Negative 4 plus 4 is 0. Now starting here, negative 2 times 3 is negative 6, plus 5 is negative 1. Now moving over to here, negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Now going here, negative 2 times 0 is 0. 0 plus 1 is 1. And then here, negative 2 times 0 plus 0 is 0. Now I also want to get this to be a 0 right there. So I'm going to go back and multiply negative 2 times row 1, but this time add it to row 3, and that's going to become a new row 3. So going back to here, negative 2 times 1 is negative 2, negative 2 plus 2 is 0, and now to here, negative 2 times 2 is negative 4, negative 4 plus 5 is 1, and then to there, negative 2 times 3 is negative 6, negative 6 plus 6 is 0, and to here, negative 2 times 1 is negative 2, negative 2 plus 0 is negative 2, to here, negative 2 times 0 is 0, 0 plus 0 is 0, and then to here, negative 2 times 0 is 0, 0 plus 1 is 1. And then I didn't change row 1, so that stays the same. So this bottom row right here actually would work better as my middle row, because I want this 1 actually to be in this spot right here. So my next operation is going to be to swap row 2 and row 3. So this isn't affecting row 1, so I'm going to keep row 1 the same. And then the bottom row now is going to become my middle row. And then the middle row became a bottom row. And then that middle, sorry, let's do the bottom row. That bottom row right here, I want that to be a positive 1, so I'm going to do negative 1 times row 3 and make that equal row 3, just to change it to a positive 1. That's a positive 1, and then a positive 2, negative 1, 0. Now, this right here is supposed to be a 0. So what I'm going to do, I'm going to change that to a negative 2 and then add it to that 2 to make it a 0, and then replace row 1. So this row operation would be negative 2 times row 2. I'm going to add that to row 1. That's going to become a new row 1. So starting right there with that 0, negative 2 times 0 is 0. 0 plus 1 is 1. Now right here, negative 1 times, or negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Now right here, negative 2 times 0 is 0. 0 plus 3 is 3. Now, right here, negative 2 times negative 2 is 4. 4 plus 1 is 5. And then here, negative 2 times 0 is 0. 0 plus 0 is 0. And then here, negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Okay. And I'm running out of room here. So the only thing left is to try to get this to be a 0 right there. So I'm going to use this, and I'm going to multiply that by -3, and then add it to row 1 to make that a 0. So this row operation, I'll do this problem in a second. Let me give myself some more room here. So this row operation is going to be -3 times row 3, add that to row 1. That's going to become a new row 1. So right here, that's -3 times 0. 0 plus 1 is 1. And then right here, -3 times 0 is 0. 0 plus 0 is 0. And then right here, -3 times 1 is -3. -3 plus 3 is 0. Now right here, -3 times 2 is -6. -6 plus 5 is -1. Here, -3 times -1 is 3. 3 plus 0 is 3. And then here, -3 times 0 is 0. 0 plus -2 is -2. And everything else stays the same. So we get the inverse from this side of the matrix now. The inverse of A Okay, finally, question number 20 from 6.4. Solving system using Kramer's rule. We did this earlier in the review. This one is now with a 3x3. So it just takes a little bit longer, but the same principle. We need to find the determinant of the coefficient matrix, and then 3 other determinants, d sub x, d sub y, and d sub z. So the determinant of the coefficient matrix, if we just take the coefficients there, we're going to have 2, 0, -1 from the first equation, 3, -1, 5, and then 4, 2, 3. So, excuse me. I'm going to expand across that row because I've got a 0 in the middle. So remember, you take the number, so like this 2 right there, and then if you cross out the row and the column containing that 2, you'd be left with -1, 5, 2, 3. And then you need to use this pattern. So that means I'm going to subtract the next number, but since it's 0, it doesn't matter what the minor matrix left over is. And then I'm going to add -1, and then again, if I cross out the row and column with -1, that leaves 3, -1, 4, 2. So then I get 2, and then if I do the determinant of that matrix, it's -3 minus 10. And then here I'm going to get 6 minus -4. So 2 times -13, that's -26. And then 6 minus -4 is 10. 10 times -1 is -10, so that's -36. Now the next determinant is going to be the d sub x. The subscript, remember, tells you that the x column, which is that column there, is going to be replaced with those numbers at the end of the equation, the constants. So the x column now is going to be 14, 0, negative 2, but every other column stays the same. And I'm going to choose to expand on that top column, or that top row again, because it's got the 0. And remember, you need to use that pattern for that top row. So 14, and then if I cross out the row and column containing the 14, I would be left with the minor matrix negative 1, 5, 2, 3, and then subtract 0, and it doesn't matter what's left over from that because 0 times anything is 0. And then plus the negative 1, and if I cross out the row and the column containing negative 1, I'd be left with that minor matrix right there. So that would be 0, negative 1, negative 2, and 2. Now the determinant of this matrix there is negative 3 minus 10. And the determinant here is 0 minus negative 2. Sorry, 0 minus 2. So let's see, this is negative 13. And, oh boy, 13 times 14, let's see. That looks like it's 182. So negative 182 plus 2 equals negative 180. All right, so now I need the d sub y. The subscript there tells us that the y column, which is the middle column, needs these numbers 14, 0, negative 2. That comes from right there. And the x column is going to stay the same as it originally was, 2, 3, 4. The z column stays the same as it originally was, negative 1, 5, and 3. This time I'm going to expand that middle row because it's got the 0. And remember, the middle row is minus plus minus. So I'm actually going to start with minus 3. And if you cross out the row and the column containing the 3, you've got 14, negative 1, and the negative 2, 3. 14, negative 1, negative 2, and the 3. Then I've got plus, but then I've got a 0, and that's just going to cancel out, and then minus the 5. If I cross out the row and the column containing the 5, I get 2, 14, and then a 4 and a negative 2, 2, 14, and then 4, and negative 2. So this determinant from that 2 by 2 matrix, let's see, 14 times 3, that's 30, that's 42. 42 minus 2. And then here I'm going to have negative 4 minus 14 times 4, that's 56. So negative 3 times 40 minus 5 negative 60 plus negative 120 plus 300. That's 180. So the D sub Z, now the Z column here, the last column is going to take these numbers. So 14, 0, negative 2, and the X column stays the same as it originally was, 2, 3, 4, and the Y column is the same as it originally was. I think the Y column was 0, negative 1, and 2. So I'm going to go back and expand on that first row again because it's got a 0 in it. And the first row, the top row there is 0, or positive minus positive. So positive 2. If you cross out the row and column containing the 2, you'd have negative 1, 0, 2, negative 2, and then I've got minus, but then it's a 0, so 0 times anything is gone, then plus 14. Cross out the column and the row containing the 14, you got 3, negative 1, and then 4, 2. So the determinant of this matrix is 2 minus 0. And then the determinant of this matrix is 6 minus negative 4. Let's see, 6 minus is 10, 10 is 144. Alright, it's 100 and, try that again, since 10 is 140, so this is 144. There we go. Okay, so x is equal to d sub x divided by d. D sub x was negative 180 divided by negative 36. That's equal to 5. And then y is equal to d sub y over d. So that's equal to positive 80, 180 over 36. That's equal to negative 5. And then z is 144 divided by negative 36. That's equal to negative 4. So